In today's class, we will see about electric potential energy. I can use P for as a short form for potential energy. Now we will consider a system of 2-point charges, say let us say Q and Q dash. Let Q is fixed at point P and Q dash is, so I'll draw a straight line. Let me say Q dash is here. This is Q dash and it is at point R. So consider a system of 2-point charges. Let Q is fixed at point P. So let Q is fixed at point P. Let Q dash moves in the field produced by Q. Moves in the field produced by Q. And let us say Q dash moves from R to some point, let me say S, R to S along a radial line PRS. PRS. So here I will mark so let me say this point is S. So Q dash is moved from R to S. Now we will say the distance between P and R is R1 and the distance between P and S is R2. R1 is the distance between points P and R, and R2 is the distance between point P and S. The magnitude of force on Q dash is given by Coulomb's law. So the magnitude of force on Q dash due to Q can be obtained by Coulomb's law. Let us say the charge Q dash is now at some point PRS we have taken. Say let me say some point RST at a distance R from P. Magnitude of force on Q dash when it is at point T is given by Coulomb's law. F is equal to 1 by 4 pi epsilon naught into q dash divided by r square. Now when q dash moves through a small distance dr, the work done is obtained by, so let me say this is the small distance dr, dr. If q dash moves through a small distance dr, then work done in moving through this distance is given by work done by the force is given by F into dr. We know F is 1 by 4 pi epsilon naught into q dash by r square into dr. If we move charge q dash from R1 to R2, that is from R to S, the total work done can be obtained by the summation of work, all these small work done, that is through small distances dr w1 plus w2 plus w3, like that we can do, or we can get it from doing the integration. The work done in moving the test charge q dash R to S, that is from R1 to R2 is W is equal to integration of dW R1 to R2. Let us do the integration. Integration of R1 to R2, 1 by 4 pi epsilon naught q into q dash by r square into dr. 1 by 4 pi epsilon naught into q dash is constant. I'll write here W equal to 1 by 4 pi epsilon naught into q dash into integration of R1 to R2, 1 by r square d square. So integrate and substitute the limits. So integration of R1 to R2, 1 by r square dr. Integration of 1 by r square, that is nothing but integration of r to the power minus 2. So recall the integration formula. You will get this as integration of r1 to r2 r to the power minus 2 dr, which is nothing but r to the power minus 2 plus 1 divided by minus 2 plus 1, and limits from r1 to r2. So you will get r to the power minus 1 divided by minus 1 limit from R1 to R2. So which is equal to R to the power minus 2. Minus sign is there. So minus of this minus R2 to the power minus 1 and R1 to the power minus 1. So this comes to, take minus sign inside, so we can write it as 1 by R1 minus 1 by R2, because R2 to the power minus 1 is 1 by R2, which is minus. So take minus sign inside, you will get this. So W is equal to Q into Q dash divided by 4 pi epsilon naught into 1 by R1 minus 1 by R2, which is equal to Q into Q dash divided by 4 pi epsilon naught into 1 by R1 minus Q into Q dash divided by 4 pi epsilon naught into 1 by R2. So now see, the work done W depends upon the endpoints R1 and R2 and not on the path. So from this equation it is very clear that the work done depends only on the endpoints and not on the path. So this can be written as U of R1 minus U of R2, that is work done is equal to the change in potential energy in moving the test charge. So where U are 1, U is of R1, U of R1 is the potential energy of test charge Q dash when it is at point R. Similarly, U of R2 is PE of test charge Q dash when it is at point yes. We can say that the work done is in moving the test charge Q dash from point R to S is equal to the change in potential energy in moving the test charge Q dash from point R to S. Work done, so we can say work done in moving the test charge, work done in moving the test charge from point R to S is equal to the change in potential energy in moving the test charge from point R to S. So work done is equal to the change in potential energy. So from the above equation we can say the P of test charge Q dash at any point which is at a distance R from the point charge Q is given by, I'll write here, Potential energy of test charge Q dash at any point at a distance r from the point charge Q. Q is given by U of r equal to 1 by 4 pi epsilon naught into Q dash divided by r. The potential energy of test charge Q dash, which it is at a distance r from the point charge Q, is given by 1 by 4 pi epsilon naught into Q dash by r. So this is the generalized formula for potential energy of a test charge which is at a distance r from the point charge.